Now, in the last few lectures, we talk about applications of mixed integer programming, how to formulate a good model and so forth, right? And then in the 2 lectures from now, we talk about that the state-of-the-art algorithm to solve mixed integer linear programs is branch and cut, right? So branch and cut basically involves branch and bound and cutting planes, right? And in the next 2 lectures, we will cover branch and bound and cutting planes separately, right? But then how to combine branch and bound with cutting planes is another very tricky question, but we won't talk about that. We will only talk about these 2 topics separately. Yeah, so well, what is branch and bound, right? We did that very quickly and show you some intuition a few lectures ago. The idea is divide and conquer, right? So let's assume you have a minimization problem C transpose X subject to X in the set capital S, where S is MILP representable, right? Of course, you could just enumerate all the possible combinations of binary variables, but that's a very trivial problem to solve, right? But then in branch and bound, what you would do is you will divide the problem and conquer each of the subproblems. Okay, so here's a very easy theorem that motivates branch and bound. Yeah, so let's assume the set S can be decomposed as a union of a subset S1 all the way to Sk. And for each of these subsets, you can solve the subproblem Zk equals to C transpose X, X into this subset, right? And the minimization problem you will get is choosing the best Zk among all the sets Sk, right? Since you are solving a minimization problem and you partition the set into different subsets S1 all the way to Sk. For each subset, you get an objective value. The minimum is obtained at the minimum over all the k. Just a very simple decomposition of the feasible region, right? So you are dividing the feasible region into the subsets and then solve each subset separately. The best solution is obtained at the subset with a minimum value. Okay, this is a trivial thing to do. Well, in order to solve MILP, again, as I said, one naive approach is to do explicit enumeration. Let's suppose you only have 3 binary variables, then you could just enumerate all the possible combinations of the binary variables. Right? From the root node, you split the nodes into x1 equals to 0, and x1 equals to 1, and so forth. You split x2 and x3. So in total, you have 2 raised to the power of 3 number of combinations. With this enumeration, as you can see, the number of nodes will grow exponentially. Right? At the end of the day, if you have n binary variables, the number of leaf nodes will be 2 raised to the power n. Okay, of course, this is not very efficient. So branch and bound is like an implicit enumeration scheme. Instead of doing explicit enumeration, you will perform some implicit enumeration, making sure that you do not skip any potential optimal solution. Okay, so in a branch and bound method, what is an upper bound? What is a lower bound, right? Similar to the algorithm we talked about before, right? Remember in things like simplex algorithm, you have a primal simplex. Maybe you can solve the dual using the simplex, then you have the primal dual, right? And in interior point method, you can get the Lagrangian dual, which is a lower bound, right? And the feasible solution is an upper bound, right? Similarly, in a MILP problem, the upper bound is provided by any feasible solution you can find. So you might think about different ways of obtaining a feasible solution. We will talk about that later. And the lower bound is provided by a relaxation. A very naive relaxation is let's just relax all the binary variables to be continuous variables between 0 and 1. Right? So that is so-called LP relaxation of the MILP problem. Okay. Now, let's think about a decomposition of the set S into different subsets. Right? So if you solve each of these subproblems and obtain a bound or a feasible solution, Z sub k, right? Then let's say Z upper this upper dash line is an upper bound on zk, and then we denote this Z underline to be a lower bound on zk, right? And then with this notation, we say Z upper line being equal to the minimization over all the Z upper line k is the upper bound on Z. And Z equals to the minimization of Z overline being the underline being a lower bound on Z, right? So let's think about for 1 second why this is the case, right? Again, in words, the idea is you partition the sets into different subsets, right? And for each of these subsets, you get an upper bound and a lower bound, right? Then now let's ask the question, how is the global upper bound and the lower bound denoted by this Z here related to the upper bound and lower bound you obtained on each of the partition, right? Okay, so why is this true, right? So this equation is saying the global upper bound is the minimum of the upper bound you obtained over all the subsets from 1 to k. Why is this the case? Yes?
It should have the lowest offset for your actual solution, since it's the minimum.
Yeah, something like that, right? Because all these upper line zk is a feasible solution of the original problem, right? Because you are partitioning the original problem into different subsets, and the upper bound you obtained in each of the subsets is a feasible solution of the original problem, right? So now the upper bound is saying, what is the best feasible solution you obtained, right? So if you minimize over all the zk, that will be saying the best feasible solution you obtained over all the set from 1 to k. Okay. And then if you look at the lower bound, right? Again, the lower bound is like a relaxation. Why is the lower bound of the original problem also the minimization over all the lower bound you obtained from all the subsets 1 to k? Right? Again, the lower bound is a relaxation of the problem, or another way to interpret that is the best possible solution you can find on this particular problem, right?
It's a relaxation.
Yeah, so can you speak a bit more?
So relaxation is optimal value will always be better than non-relaxed because the feasible region is big.
Yeah, so if you partition them into different subsets, right? So the best potential solution you find is a minimum over all the subsets, right? Because if you give 2 nodes, one gave you a lower bound of 10, the other gave you a lower bound of 8, right? Suppose you are minimizing, then the best possible solution you can find for the full problem is 8, right? Because in one of the nodes, potentially you can find a bound that is 8. Okay, so let's show some concrete example. This might be a bit abstract, right? Okay, so let's think about this particular problem where let's assume at the root node, you solve the LP relaxation and you get a lower bound of 13, and somehow you have a heuristic which gives you an upper bound of 27. Okay, so now let's say after solving the root node, you will do an operation called branching, right? Let's pick one variable and split the original problem into 2 nodes. Then you solve problem S1 and S2, where in S1 you add the constraints x1 has to be less than or equal to 0, and on the right-hand side you add a constraint x1 is greater than or equal to 1, assuming x1 is a 0, 1 variable. Okay, now you solve these two nodes, S1 and S2, right? You got the upper bound and the lower bound. Right? Again, upper bound is a feasible solution you'll find at this node. Lower bound is a relaxation you solve at this node, right? The reason the lower bound increased from 13 to 20 is because you add one additional constraint that improve the lower bound, right? And similarly, you add another constraint, x1 equals to greater than or equal to 1, the lower bound also increase, right? So after you branch, the lower bound is always going to improve, right? Now, what is the upper bound for this problem now? After you branch? 20, right? Because the feasible solution you find at S1 is 20, and the feasible solution you find at S2 is 25, right? So therefore, the best feasible solution you find on all the nodes is 20, right? So you could say at this stage, the upper bound is the minimum of 20 and 25. So this is 20, right? And what is a lower bound for this problem at this stage? 15, right? Because again, conceptually, lower bound means the relaxation on this particular node, or the best potential solution you can find, right? Since at this node, the best potential solution you can find is 15, then the global lower bound is also 15, right? So that means across all the nodes, what will be the best possible lower bound you can find? Okay. Now, let's assume this problem has a large number of binary variables. We only branch on x1, right? So now the question is, do we need to continue exploring this node S1? No, right? The reason is this node has already converged, right? Because if the upper bound equals to the lower bound already, so this is called pruned by optimality. Right? Because at this node, you already have the upper bound equals to lower bound. You know this upper bound 20 is the best feasible solution you can find on node S1. Okay. So therefore, with this pruned by optimality, you can save a large number of enumerations, right? Because after you just did one branching, this whole node get pruned, right? So let's suppose you have n binary variable, pruning S1 will avoid further branching on S1, right? Potentially saving the time to solve additional 2 raised to the power of n minus 1 LPs, right? Because you just branch on one variable, you can potentially branch on 2 raised power of n minus 2 LPs using explicit enumeration. Okay. So a special case of pruned by optimality is so-called pruned by integrality. So that means when you solve the relaxation at a given node, the solution to the relaxation satisfies all the integrality constraints. Okay, so in that case, why can you prune by optimality if the solution to the relaxation is integral? Yes?
So whenever we're branching, why don't we include the node that we're branching from as part of the upper bound, lower bound considerations?
Yeah, because the upper bound and the lower bound can always improve, right? So at least the lower bound can always improve because you add this additional constraint, right? You are adding more constraint, the lower bound is a relaxation, right? After you add more constraint, the objective will always increase, right? And you can think about the upper bound as I'm going to inherit the solution you got from this node, and then I'm going to try to find some new solution here. But you could also think about the upper bound as taking the minimum over all the nodes, right? So let's say we take the minimum of 20, 27, and 25, right? But the lower bound will always improve. You only need to consider the lower bound at the leaf nodes. Right?
So even though it's increasing here and we're looking for the minimum one, that's fine.
Yeah. So you only consider the lower bound at the active nodes per se. You have already branched this node. Okay. Now let's come back to my question here, right? So when you solve a relaxation at a given node, right? Let's assume you are solving the root node relaxation. After you solve the root node relaxation, all the binary variables are binary, right? So why can you fathom by optimality?
Isn't it the same as saying that this is upper bound and the lower bound at the same time?
Yeah.
Because if it's in all the integral, it means it's also your upper bound. Since
Right,
it's
right.
feasible for
Yeah, exactly.
So it's almost the same as
Uh-huh.
previous.
Yeah, exactly, right? So because you solve the relaxation, you know that the relaxation is a lower bound, right? And the same solution happens to be feasible, right? A feasible solution gives you an upper bound, and then that shows the upper bound equals to the lower bound in that case. Okay. Now there's another way of pruning the problem. So let's assume here, right? We after we branch, we get upper bound 20 and lower bound 18 in the first node. And in the other node, you got upper bound of 26 and the lower bound of 21. Right? Now the question is, can you prune any of these two nodes? Right? So here, as I said here, node 2 can be pruned. Why is that?
Because it's lower bound, higher than upper bound for this one.
Yeah, exactly, right? Because the lower bound means the best possible solution you can find on node S2, right? It's 21, right? Even if you continue branching on node S2, the best possible solution you can find is 21, right? But you already find a solution of 20 at the other node. Therefore, you don't need to continue branching on S2. There is no way you can find a better solution than 20, than 21, right? Okay, so here, as you can see, you find a feasible solution of 20. Therefore, it makes no sense to continue exploring S2. And the special case of prune by bound is when you solve the relaxation, it is infeasible. Right? So if a relaxation is already infeasible, that means there is no feasible solution. Right? If you add integrality constraint, there won't be any feasible solutions. This is called prune by infeasibility. Okay. So basically, these two things are the tricks you will be using to reduce the number of nodes in branch and bound compared with explicit enumeration. Right? Prune by optimality and prune by bound. Okay, so with that, how does the branch and bound method look like for MLP? Right? So here I'm showing you a pseudocode. The first step is to initialize the problem. Let's solve the root node relaxation as 0. And then we add it to the list of active subproblems, right? Why do you keep this list of active problems? This list keeps track of all the nodes that have not been pruned yet. Right? For example, here, at this status of the branch and bound, you only have one active node, S1. Right? This node has been pruned. This node has been branched already. Right? So this active list A keeps track all the active subproblems. So if there are no active subproblems, right, either they have been pruned or they have been branched, then you can stop the algorithm, right? Or if the upper bound is plus infinity, we say P is infeasible, okay? So if there are still active nodes in this active node list, you just pick a problem from this active list. Right? For example, in iteration 1, you will select the root node, right? Because in the initialization, you are putting the root node relaxation to the list. Right? So you can imagine in the first iteration, you will just choose the root node. Right? Let's choose the node from the active node list according to some what we call node selection rule. Right? Why do we need a node selection rule? It is because if this list has many nodes, right, which node are you going to choose? Right? So let's suppose at some point if you did some branch and bound, right, there are in total 3 active nodes. They have not been pruned yet. Then which node are you going to choose to continue branching? Right? That's what this node selection rule means. Now, after we select a node, we will perform this step called lower bounding. Right? So if you choose a node, you will solve the relaxation corresponding to that node. Right? Let's say if you choose the root node, you will solve the linear programming relaxation. And then if you choose other nodes, that just solve its relaxation. Right? And the lower bound at this particular node is nothing but the objective of the relaxation. Okay. Now, after you solve the relaxation at node Si, right? Let's denote this by Z underline I. Many cases could occur, right? If the lower bound you find at this particular node is already greater than or equal to the global upper bound, right? So Z overline is a global upper bound. Then you can discard node Si, right? So this is like pruned by bound or pruned by infeasibility. Right? Since the lower bound you find at this particular node is already worse than the best feasible solution you find so far, then you can get rid of that node. Okay. Now the other case is when the lower bound is strictly less than the global upper bound, right? That means potentially you can still find better solution than the global upper bound, right? And in this case, if this x prime happens to be integer, right? If x prime happens to be integer, as I said, we can prune by optimality, right? Because the relaxation is feasible. Now you can update the global upper bound to be this feasible solution you just find. Okay. On the other hand, if the solution you find is better than the global upper bound, but the solution is not feasible, right? X prime is not integer, then you have to continue. This node cannot be fathomed yet. Okay. Any questions here? So if you read line by line by the pseudo code, that should be easy to understand. But the high level idea is after you choose a node, you will solve its relaxation, right? If the relaxation is too bad, it's already worse than the global upper bound, you get rid of that node because you cannot find better solutions. If the node is better than the global upper bound and the solution happens to be feasible, then you can update the global upper bound. Right? Otherwise, you have to continue. With a lower bounding step, there is also an upper bounding step, right? And it's optional. You don't have to do that because at some point, the solution will be feasible if you keep branching, right? But typically in MLP solvers, there is also an upper bounding step. You will perform some heuristics, right? If you find a solution to a relaxation, it is not feasible, then you can do some very simple heuristics, right? Well, very simple heuristic, you will just do rounding, right? Let's round all the binary variables and check if the problem is feasible, right? If it's feasible, then you find a feasible solution. The other heuristic is you can do some sort of local search by solving a sub-MLP problem. Okay. And step 5 is prune by bound, right? You can discard all the nodes whose lower bound is greater than or equal to the global upper bound. Right? So you cannot find a better solution in those nodes. Okay. And next step is branching, right? So if you already solved the relaxation at this node Si, right? And suppose it has not been pruned, then what you can do is apply a branching rule to node Si and generate new subproblems. Typically, we just generate two new subproblems. Right? Let's select a variable and branch it to 0 or 1. Okay. That's a pseudocode for the branch and bound algorithm. Yes.
In the step 3,
Yeah.
Where we are saying if x prime is not integer, so possibilities are x prime is either 1 or 0, right? Because we are just considering binary.
Uh-huh.
So, but if we have Zn, then it can be an integer.
Yeah.
Is that what it means?
Yeah, exactly, right. So here it is solving a general mixed integer linear program, but typically all the MLPs are binary MLP. You can say they are not binary. Yeah. Most of the problem you encounter will be binary. Okay. Any other questions? Okay. Now, if you look at the pseudocode, there are two things we skipped. One is the so-called node selection rule, right? If you have many active nodes, which node you should select, right? So just like in this case, there are 3 nodes here. Which node should I select for solving the relaxation? The other thing is so-called branching rule, right? After you solve the relaxation at node Si, let's suppose there are many variables that have not been branched yet. Which variables do you select to branch? This is called the branching rule. Okay. So let's talk a little bit about the commonly used node selection rules and the branching rules. I remember when you asked this question last time, right? So when you do branching, should you do depth first search or breadth first search or some other heuristics, right? So depth first search means that you should go as far as possible down a branch before backtracking. Right? So that means after you branch, you should keep down branching on node so that it goes down the branch and bound tree as fast as possible, except expanding the width of this tree. Okay, so this is like a depth first search. Right? The nice thing about depth first search is you will be able to quickly find a feasible solution, right? Because the more you branch down the tree, the easier you will be able to find a feasible solution since you are fixing a large number of binary variables. Okay, so this helps prune by bound or optimality, right? Now the other commonly used branching rule is called best node first. That means among all the active nodes, I'm going to select the node that gives the tightest or lower bound. Oh, actually, well, it depends on how you define tight here. It will pick the node that gives you the minimum lower bound, right? Remember, the lower bound of the full problem is a minimum of the lower bound over all the active nodes, right? So if you choose the problem that gives you the smallest lower bound, your global lower bound will always improve. Okay. Again, so let's assume we have some active nodes here, which gives you a lower bound of, let's say, 10, 15, 20, 16, and 18, right? Okay, so if you have these active nodes, the global lower bound is this node here, right? Gives you the lower bound of 10. So 10 gives you sort of the best relaxation you can find, right? So the 10 would be the global lower bound, right? So if you branch these particular nodes into 2 nodes, this lower bound 10 will be improved. That will also improve the global lower bound, right? So this is so-called the best node first node selection rule. Okay. Now what about branching rules? Which, after a node is selected, which variable should we branch on? A very naive branching heuristic is to branch on the most fractional variable. What does most fractional variable mean? You can consider the variable whose value is closest to 0.5. Right? Let's assume all the variables are 0, 1 variables. Right? If their value are close to 0 or 1, maybe they are already close to being binary. Right? So if a variable value is 0.1, maybe you round it down to 0, then it doesn't affect that much. Right? But if a variable value is 0.5, you don't know which way you should round. Right? The most fractional variable being the variable whose value are closest to 0.5. Right? So you could calculate the fraction of a variable using this formula, xj star minus the floor of xj star. And similarly, you could calculate the so-called apt fraction by 1 minus fj. Right? So you choose the variable whose value fj is closest to 0.5, right, as the most fractional variable. The rationale is we will try to make those variables less fractional. Right? So if they are very fractional, they are not close to the 0, 1 value. Okay. The issue with most fractional variable branching is it does not consider the improvement in bounds. Right? So the most fractional variable branching will consider the feasibility of those binary variables, but it does not account for, after I branch, how much my lower bound will improve. Right? Maybe some of the variables are more important than other variables in your optimization problem. Right? So this was not considered in the most fractional variable rule. Okay. The other, I wouldn't say commonly used, but sort of a golden standard in branch and bound is so-called strong branching. Okay, so let's now look at the text now, right? Just talk about the conceptual idea. So strong branching means at a given node, let's assume I still have, let's say, m fractional variables. I will try to tentatively branch on each of these fractional variables and see, after branching, I resolve the two problems created by branching, and you use the variable that gives you the best bound improvement. Okay, so what does that mean? Again, let's not go to the notation, but maybe showing you a very concrete example. So let's say at this particular node, I have two fractional variables, x1 and x2, right? Let's say x1 equals to 0.3 and x2 equals to 0.5, right? So strong branching would do the following. I will tentatively branch on x1. Okay, and then supposedly after I branch on x1, I got the lower bound to be, let's say this is node 1, node 2, 10 and 12, right? And similarly, I will also branch on x2. And now I solve these two LP relaxations and get a lower bound of, let's say, 9 and 13. Okay. So I've tentatively branched on all the fractional variables. And as I said, which variables should I use at the end? I will pick the variable to branch that give you the best bound improvement. So in this case, which variable gives me a better bound improvement?
X1.
Why do you say that? Yeah, you say someone say you say x1, you say x2. Yeah, so that's yeah. So why do you say that?
That gives a better lower bound.
Again, you want to improve the lower bound, right? The lower bound higher is better, right?
We
So
wanna
on that-
maximize the lower bound?
Uh-huh.
Yes.
Oh.
Yeah. So you see, the lower bound at when you branch on x1 is 10, right? Because you are taking the minimum of the lower bound, right? And in x2, the minimum of the lower bound is 9, right? So therefore, if you branch on x1, it gives you a tighter lower bound, right? So you want to improve the lower bound as much as possible. So therefore, you want to branch on x1.
Okay. So we
Okay.
always use the lowest lower bound.
Yeah, so you will use the lowest lower bound to calculate the lower bound for this particular problem,
Okay.
right? But then you would want to get lower bound as high as possible, right? Okay, so that's a tricky thing. So therefore, in strong branching, you would tentatively branch on all the fractional binary variables, right? So it is a very expensive step because you need to solve the number of fractional variables times 2, many number of linear programs. Right? In this case, you have 2 fractional variables. You need to solve 4 linear programs in order to estimate the improvement. Okay, and then at the end, you will pick the one that gives you the maximum lower bound among the minimum of the 2 branches. Okay, 2 nodes you just created, right? So the lower bound, this minimization means in order to calculate the lower bound, you need to take the minimum of these 2 values, right? The minimum of these 2 values. But which variable you are going to choose will be the maximum over the minimum of these 2 nodes, right? Okay, so in this case, the J star equals to 1 here. Okay, so if you are confused, you can take a look at this example. So why do we want to use strong branching, right? It's a quite expensive step, right? In the most fractional variable branching, you don't need to solve additional LP, right? Pick the most fractional variable, just solve 2 LP and continue. But in this case, in order to decide which variables you are going to branch, you need to first solve a large number of LPs, right? To sort of do a probing on which one will give you the best bound improvement. Okay, but then the advantage of strong branching is that it usually gives you very small tree size. Right? Since you already tried branching on all the possible variables and see which one gives you the best bound improvement, empirically it reduces the number of nodes in branch and bound. But con, as I said, is you have to solve 2 times C being the number of fractional binary variables in order to decide which variable to branch on. Okay, so now let's say strong branching is quite expensive, right? But how do we sort of alleviate this issue here? One of the solutions to mitigate the cost of strong branching is so-called pseudo-cost branching. Let's not look at the math for now. Right? The idea of pseudo-cost branching is let's just run strong branching for a few iterations and see what happens, right? Because if you run strong branching a few iterations, you will tentatively branch on most all the variables, basically, all the fractional variables, right? Let's say at the first iteration, you are going to branch on all the fractional variables, right? And then let's record the bound improvement after branch on each of the variables and assign them the so-called pseudo-cost, right? And then at the later stage, you do not branch on those variables again. Just use the pseudo-cost as a surrogate for the strong branching bound improvement. Okay, that's a very high-level idea, right? Maybe let me also draw you a picture here, right? So let's say this is a root node, right? At the root node, we did strong branching, right? And then we sort of get a bound improvement by branching on all the fractional variables, right? And then we just take the the ones gives you the best bound improvement, right? So let's say this is x3. Right, so assuming you have variable x1 all the way to x5, right? So at the root node, you did strong branching and decided to go with x3. Now, let's assume at this node, I still have 4 fractional variables, right? So x3 has been branched out. Maybe my x1, x2, x4, and x5 are still fractional, right? Now, instead of doing strong branching all over again, I'm going to use the bound improvement I got at the root node. Okay, that's a tricky point, right? So if you were to do strong branching at this particular node here, right? So if you do strong branching here, you will need to solve 4 times 2 LPs, right? Because after you branch on x3, maybe the rest of the 4 variables are still fractional. Okay, so you still need to do 4 times 2 LPs, considering this constraint you have already added, right? But recall that we already did strong branching at the root node. We solved 5 times 2 LPs at the root node already, right? Okay, so now the argument is saying, instead of solving additional 4 times 2 LPs, I'm going to use the bound improvement I got at the root node as a surrogate as a surrogate of the strong branching score at this particular node. Okay, so I'm not saving some time in solving additional LPs, but of course, this sort of pseudo cost I got using the strong branching scores at the root node is not very accurate, right? Okay, so pseudo cost branching means I will run strong branching for a few iterations and record the bound improvement for each of the binary variables. Maybe you can take the average of the bound improvement over the iterations and use them as a surrogate instead of doing strong branching at each node. Okay, so that's sort of the idea of strong branching. No, pseudo cost branching. Okay, so how do you calculate the pseudo cost? Right, the idea is the following. At a particular node, let's assume at this particular node you solve the LP relaxation, and then let Zj minus be the cost when you solve the LP with xj less than or equal to the floor of this integer value, and Z plus being the right branch, right? So now you can calculate the pseudo cost by saying, if I branch to the left, then the lower bound will improve compared with the relaxation at the current node, right? So this is an improvement in bound, right? In here, right? And then the denominator is the fraction of the variables you have, right? So this value kind of denote after you branch this variable, how much will the objective improve per, let's say, unit, let's say per unit perturbation in this binary variable. Okay, and similarly, you can define the improvement for branching to the right. Okay, so this is a pseudo cost. And a given node, you can use the pseudo cost to estimate the bound improvement rather than doing a strong branching. And that's the idea. You can read the math in detail later, but the figure I show you kind of gives you the intuition. Okay, so those are the commonly used branching heuristics in branch and bound. Another topic I would like to talk about briefly is so-called branching priority. Okay. In some of the problems, the user may have a very good idea on which variables we should branch on first compared with the other variables. Maybe give you an application of that. remember we have this so-called unit commitment problem, right? Where the binary variable u describes whether a generator is operating at time t, right? So u can be 0, 1 variables. And there is y and z variables, which describes the startup and shutdown of those generators, right? So now the key observation here is if you fix all the u variables, all the y and z will be automatically fixed, right? Conceptually, let's say if you have some variable determining whether the generators are on or not, right? And when a generator switch from off to on, then the variable YGT has to be 1, right? Because they have to start up to turn a generator from off to on. And similarly, when a generator switch from on to off, then this binary variable ZGT should be 1, okay? So after all the U variables are fixed, the Y and Z will be automatically fixed by propagating through the constraints, okay? So therefore, in this problem, perhaps you could cite branching priority as you will branch on the U variables first, rather than on the Y and Z variables. And in other problems, there are similar observations, right? Basically, the idea is if you fix part of the binary variables, usually those binary variables have a very small number. After you fix a very small number of binary variables, the rest of the binary variables will be automatically fixed through constraint propagation, right? Then you should first branch on this very small number of binary variables, right? To avoid branching on the other set of very large binary variables, okay? In order to set this, you could use, okay, actually in the solvers like Groovy, you could set the branching priority on some of the binary variables, right? And this can be very effective when you solve especially some of the scheduling problems, right? Okay, just to keep this in mind. The other special issue related to branching rule is on the so-called special ordered sets, right? So I want to use this opportunity to talk a little bit about something called special ordered sets. You will see this in the literature from time to time. There is a so-called special order set type 1, or SOS1, right? The idea is if you have X from 1 to K as the binary variables, a special order set means the summation of all the binary variables equals to 1. Right? You will see this type of constraints very often in optimization problems. Can someone give me an example when this problem is used? This special order set 1 is used. Okay, so one example is in the big M formulation of disjunctive programs, right? So remember, disjunctive programs is representing a union of polyhedral set, right? You are saying my feasible region is in one of these polyhedral set, right? So then you need a variable, binary variable, to represent whether my binary variable is in this, or that set. You need 3 binary variable to represent 3 polyhedral set, right? And then this logic means I'm only going to be in one of these polyhedral sets, right? So therefore, you have this type of constraints here. Okay, and then let's assume if K is a large number, then you will have a very unbalanced branching rule if you use the standard branching rule. So why is that, right? Because let's assume if you use the standard branching rule, okay? Let's assume K equals to 10 here, right? Now, without loss of generality, let's assume we first branch on X1. Okay. What's the issue with this type of branching, right? Why do I say it will be a very unbalanced branch and bound tree?
There more leaf nodes on the right.
Yeah, right, exactly, right? So if you fix x1 to 1 here, right? Because of this constraint, all the other variables are automatically set to 0. Okay, yeah, so therefore you will always expand on the left, right? Whenever you set a variable to 1, all the other variables are automatically equal to 0. Right? So that's why this is a very inefficient branching rule here for S1 type of constraints. So what is a more efficient branching rule is you will set a subset of variables from I from 1 to R to 0. And the other branch is setting all the rest of the binary variables to 0. Okay, so let's think a little bit about that. Okay, why these are two disjoint set. Okay. Yeah. So the idea of this branching rule is saying whether the variable that is equal to 1 is on the first part of the sets or on the second part of the set, right? So among all the binary variables, there can only be one variable equals to 1, right? The rest will be 0, okay? So what this set means is, in words, is the variable that equals to 1 is not in the first R variable. Right, because this set is setting the first R variables to 0. Right? I is from 1 to R. Okay, and the second set is setting all the variables from R plus 1 to K equals to 0. Right? So this set is saying basically the variables that equals to 1 is in the first R variables. Right? It set the rest of the variables to 0. Okay, that's a logic here. The thing is that with this branching rule, you will have a very balanced branch and bound tree, right? Since you are sort of breaking the problem in the middle, right? Where R is the first, the summation over all the xj's, such that when for the first time the summation is greater than 1 over 2. Okay, so this is like the counterpart of the most fractional variable type of branching rule applied to SOS1 set. Okay, so this is like a heuristic on how do you set the R. Any questions here? Right? Yeah, again, the idea of this branching rule is saying, let's think about conceptually, right? How do we branch, right? Instead of just pick a variable and branch, because we have this SOS1 constraint, we know that only one of the binary variables will be 1, right? So now let's just break down this set into two parts, right? So let's say we have 10 binary variables. Maybe let's assume R equals to 5, right? Let's consider the first 5 binary variable x1 all the way to x5, and the rest of the variable being x6 all the way to x10, right? So the way we branch is saying, one branch is saying the variable that equals to 1 is not in the first 5 binary variable. It must be in the last 5, right? Then the other branch is to say the variable that equals to 1 is not in the last 5 binary variable. It must be in the first 5, right? So that's sort of the conceptual logic here. And then reflected in math, it will be these two sets. Okay, and then as you can imagine, there is another thing called SOS2 type of special order set. It has very wide applications in mixed integer linear programming as well. because it can represent piecewise linear functions, right? So you might be wondering, right, if you have a non-convex function, how do you approximate a non-convex function, right? And let's assume you have this particular function, like a sine function, right? But you still want to solve this problem to global optimality, right? We will talk about how to solve non-convex problem to global optimality, but here's one of the ways to approximate non-convex problem using mixed integer linear programming constraint, right? We will do a piecewise linear approximation of the non-convex function. I just pick some breakpoints here and then connect them by piecewise linear functions, right? Another question is, how do we represent these piecewise linear functions, right? Okay, so let's think a little bit about for a second, right? Again, you of course you need to use some binary variables, right? Okay, so the binary variable is basically specifying which of these line segment my x values is in, right? So if your x value is in this line segment, you are going to use this piece, right? If you are in a different line segment, you will use a different piece, right? So that's sort of the logic here. How do we represent that using so-called SOS2? Okay, the way to do that is the following. Let's assume x superscript I are the breakpoints we have chosen so far, right? So x superscript I are those x on the x, they are x1 all the way to x5, right? You have chosen 5 different breakpoints, right? And we will get a function value at these 5 breakpoints, right? And let's assume x is a combination of those breakpoints, right? Okay, so here I'm taking all the combination over all the breakpoints, right? But the constraint we need to enforce here is, if I pick a particular x, only the adjacent x's have a non-zero lambda value. Okay, so again, I'm choosing x to be a combination of x1 all the way to x5, right? So this is like a Kornik combination, let's put it that way, right? But if you pick a particular point here, right? So this is my x. I only want x to be a combination of x2 and x3, right? The 2 adjacent breakpoints, right? Because I want to use this piece here. I don't, if I'm at this particular point, I don't want to use this piece here, right? That's not going to be accurate, right? So I just want to use this particular piece here. So how do I force x to be a convex combination of these 2 breakpoints instead of a convex combination of all the breakpoints, right? So this is where SOS2 comes into play, which says, let's consider a set of variables which at most 2 can be positive, right? If 2 are positive, they must be adjacent in the set. Okay, so that's what SOS2 means, right? If consider all the lambdas, right? If I pick a particular point here, I only want these 2 adjacent lambdas to be positive, right? All the rest should be 0, right? Similarly, if I pick a different point, x here, I only want it to be 2 adjacent, to be a convex combination of the 2 adjacent x. Right? That's what SOS2 constraint means. Great. And the adjacency conditions can be enforced by the solution algorithm, right? Almost all the commercial solvers allow you to specify SOS2 constraints, and of course it can leverage branching rules tailored for the SOS2 constraints, right? So one takeaway from this slide is, whenever you want to approximate a non-convex function using piecewise linear function, try to remember SOS2 constraint, right? You should formulate the problem in this way, right? I'm sure there are many applications if you work on especially chemical engineering problems. There are many non-convex functions, right? So let's assume you don't want to directly solve the non-convex problem, then you could use piecewise linear approximations and then leverage MLP solver. Right? And that's the practical application of SOS2. Yeah, and then I give you some examples of SOS2 in Groovy and then implementation in Pyomo. Oh, so one of the last thing I would like to talk about is symmetry. Right? In many problems, especially combinatorial optimization problems, it could have a lot of symmetry. Right? Let's say a graph coloring problem. The idea is you want to color the nodes in a graph. Right? You could color them using different colors, let's say red, green, and black. Right? But then the colors are indifferent to you. Right? If you switch the colors of two nodes, then it doesn't matter that much. Right? Maybe for example, I give you a graph. Let's say a problem can be like this. Right? I give you a given, maybe not drawing in red. Okay, I give you a very simple graph here. Right, so I have 5 nodes in this graph. Now the question of graph coloring, one of the graph coloring problem could be, I give you the opportunities of color the nodes to red or to green. Right? All the nodes have to be either color red or green, such that the adjacent node should have different colors. Right? So I cannot cover these 2 nodes to be both red. Right? Then the adjacent node would be both red. Right? So the question would be, you could color the nodes in a way that the adjacent nodes have different color. Right? But now it doesn't really matter whether I cover the node to be green or red. Right? Green and red are symmetric in some sense. Right? If I have a solution to that problem, let's say I randomly color this node. Let's say if I can find a feasible solution, right? So let's color this by green, and this is green, right? So then I color these 2 nodes by red, right? So this is a feasible solution to the graph coloring problem I just mentioned, right? And now a symmetric solution is saying I will flip the red and green in this solution. That is still a feasible solution to that problem. So in this case, green and red has some sort of symmetry. Right? Okay. And another problem is in, let's say, room assignment. Right? For example, I don't know if Purdue is solving a mixed integer programs to assign classrooms. Right? So how do you assign classrooms here? Right? The way you would want the problem to be feasible is that hopefully all the students have registered for the class. Right? There should be some non-overlapping constraints, right? There could not be 2 classes happening at the same classroom, right? The time should have no overlap. And hopefully, the students who took the class will also have no overlap, right? If you register for 2 classes, they should not be happening at the same time, right? So that's sort of the assignment, a room assignment problem we are going to solve, right? Actually, I don't know how they solve that, hopefully by some algorithms, right? And now the issue is, do we really care about this class is assigned to this room or that room across the hallway, right? If the class is at the same time, because that classroom is sort of identical to this one, right? So we don't really care about that, right? This problem also have a lot of symmetry, right? Since basically all the classrooms on this floor are identical, right? Then we will have a huge number of solutions that are identical. With those identical solutions, as you can imagine, if you are doing branch and bound, you are going to explore very similar solutions while you are doing branch and bound, right? The thing is that you always want to improve your solution instead of encountering the same solution again and again, right? Okay, so that's sort of the symmetry in mixed integer linear programs. Here's a very trivial example to show you the case of symmetry. Right? You have 6 variables in this problem, x1 all the way to x6, and then you have constraints on x1 to 3, and then you have constraint on x4 to 6, and this is another constraint. Right? So the objective coefficients on the first three variables are the same. On the last three variables are also the same. Right? So it's very easy to recognize x1, x2, and x3 are interchangeable. x4, x5, and x6 are interchangeable in this problem. Right? A more specific example would be, let's consider this particular solution. Right? x1, x2, and x3 equals to 0, 0, 1, 0, 1, 0, and 1, 0, 0. All these three solutions are identical. Right? They do not change the value of the problem. And similarly, these three solutions are also identical. Right? But then if you use standard branching rule, they are not aware of this symmetry. Right? You could be, after you branch, you could get exactly the same solution all over again. Right? So we want to avoid this issue. Right? A very trivial solution is to add symmetry breaking constraint. Okay, so the symmetry breaking constraint looks like this. You can set a priority list of all the variables. Let's say x1 greater than equals to x2 greater than equals to x3. So in that case, if x3 is equals to 1, that means x2 and x1 must have already been selected. Right? You can think about, let's say, a room assignment problem. The logic I'm going to use is that you are trying to assign classes to classroom. I can enforce a logic saying that this classroom has to be first selected before all the other classrooms on this floor can be selected. Right? Or you could set a hierarchical list on this floor. Right? Let's say number this classroom as x1, the other as x2, and one more as x3. If I add x1 greater than equal to x2 greater than equal to x3, is that I'm setting a priority list of selecting the classroom when I'm doing cross assignment problem. Right? Okay. And then there are other applications. Let's say you want to decide which generators are going to generate power in a particular hour, right? So let's assume there are three identical generators owned by the same company, right? Then you could say, if I need to generate power, my priority is that I will turn on the first generator in the first place, then the second, then the third, rather than asking the algorithm to pick randomly among them. This can greatly reduce the number of symmetric solutions. Okay, any questions here? Yeah.
How do we know that there is a symmetry apart from just kind of logic or inspection?
Okay, yeah. So that's a great question. The easiest way is logic impression, right? That is the easiest thing to do, right? You have some engineering intuition, you set a hierarchy on those problems. But mathematically, it is a very deep concept in general to find symmetry in integer programs. So there is maybe I could add a reference here. There is a textbook called 50 Years of Integer Programming. And in that textbook, there is one chapter on symmetry. Okay, so I remember when I was taking an integer programming class, they asked each of the students to do a course project, and I did that chapter on symmetry. Right? But then if you are curious about symmetry, that chapter is very dense to read. There are a lot of mathematical concepts within that, but I'm just giving you probably 1% of that chapter, which is very intuitive symmetry breaking constraints. Right? If you want to do symmetry in general, there are a lot of theory out there. Yeah. Okay. Another topic let's talk about real quick is so-called pre-processing and pre-solve. If you read the Groovy log file, you will find out it says that pre-solve eliminates this number of variables, this number of constraints, and so forth. Right? So usually the pre-solve can do things like heighten the variable bounds, remove the redundant constraints, and then it will help you fix some of the variables that are inferred by some logic constraints. Yeah, and then of course, doing pre-solve will help you reduce the problem size and will help branch and bound as well. I can talk a little bit more about that. In one of the lectures, we will talk a little bit more in detail on mixed integer programming solvers to give you some sense on how the state-of-the-art solvers work, right? Of course, it's not just branch and bound and cutting planes. There are a lot of techniques inside the box in the modern solver. And then you can change all those settings in the solver. Okay, and then, so if you are interested in the details, you could read this integer programming textbook. And some part of this lecture actually comes from a PhD thesis by Dr. Achterberg. I think now he is maybe the VP at Groovy. He developed integer programming and constraint programming solver, which is probably still one of the best integer programming solver nowadays, but someone else is maintaining that, right? Basically, his whole PhD thesis is on developing a solver, and then in the PhD thesis, he did a very nice review about different branching heuristics, node selection heuristic. I couldn't find a better reference than a PhD thesis. Usually people will just cite his PhD thesis when people talk about things like pseudo-cost branching, reliability branching. So you can check the introduction section of the PhD thesis. And again, if you are interested in very specific topics like symmetry, you could check this textbook called 50 Years of Integer Programming, where they invited many integer programmers to write. Each of one of the integer programmer will write one of the chapters. For example, there are chapters on semi-definite programming relaxation for combinatorial problems. There are other more like computational aspect of integer programming. Just some very good bedtime reading, right? If you want to fall asleep quickly, you could take a look at this textbook. Okay.